Okay, so welcome back, everybody. Just going to jump right into it from yesterday's lecture. We ended with an example showing how our discussion on Markov chains so far allows us to generalize. We started with having two states that had some sort of, we thought of it as population distribution. Now we're quickly going to see that, using state here in the geographical sense is actually not accidental, because you could also think about this as state, as in state of being, which is more frequently how we're going to be thinking about it for more generalized problems, but still we can think about these as geographical states. So we had an example of two states. We generalized what it would look like having three states. This diagram indicates at each step how the distributed population is moving. So this diagram allowed us to write up what we call the transition matrix, the entries in the transition matrix. Remember, we're tracking, so T sub 1, 2, so that is this entry here, was tracking the proportion of people at each step that moved from state 2 to state 1 in one iteration. Okay, now each of these entries is for one iteration. The reason I keep repeating this will be made clear later. So that is this entry. The fact that the diagonal entries are these indicated by the loops here in the diagram is that this is T sub 1, 1, so this is the proportion of people transitioning from state 1 to state 1 in one step, right? So that's the same as the people staying in the same state. Okay, so this was how we set up this example from yesterday. Now, given this example, let us pick our favorite maybe initial population distribution. So let's pick, let's say, given some initial vector looks as followed, or as follows, looks like this. What does this tell you? It says if I have a population distribution, a total population distribution of 1, so the total population is 1, that 1 is distributed amongst the three states. Here's state 1, state 2, state 3. So 70% of the population lives in state 3, 10% of the population lives in state 1, 20% of the population lives in state 2. Okay, that's what this says. Now, if we hit this with the matrix T, what do we get? So this is approximately, if I multiply this out, this is approximately 0.2500. I'm writing this out because we were actually interested to see how this distribution moves about. So you see that even after the first step, my distribution now has changed in this way. So distribution of state 1, or the amount of, say, people in state 1 has more than doubled. And look at how this has decreased. But look at this from the point of view of the example. Only 70% of the people in state 3 are staying in state 3. And 20% of them move to state 1, 10% of them move to state 2. And state 3, according to this, in this particular example, began with more people. So that 20% is a lot of people. In fact, it's, even at this step, that's more than twice the amount of people that originated in state 1. Okay. Iterating this to see, if we thought about this occurring over a year, for instance, seeing what happens in the next year or the next time step, whatever that amount of time is. What about t squared times x naught? So this is, I would have the matrix T multiplied by itself and then multiply that by my vector. This will give me the following. This is 0.3512, 0.2512, 552, and 0.3934. Let's do one more, and I want to put it here so that it's on the same page. So I'm going to do t to the 5 times x naught. What is that? So this would be at the fifth step here. This is 0.5007, 0.2692, and lastly 0.2302. Now, notice how this has changed from the original distribution. Now I have substantially more people existing in state 1. I have slightly more people existing in state 2, and then substantially less people existing in state 3. But if we interpret this diagram properly, that's not surprising at all, right, given how this is set up, right? 20% of state 3 is leaving at each step, and state 3 began with more. So, but here, you might think about this intuitively and say, well, you know, in a way, maybe I expect this process to settle eventually, so that after some number of time steps, it should maybe remain the same. Now, at first you'd say, well, wait, depending on the setup, maybe that's not the case, right? Maybe you think up a transition matrix where this thing never quite settles. And in fact, that could happen. But you might look at a situation like this and say, hey, I think this might actually settle down, so that eventually my matrix iterates here, so t to the 10, t to the 100, it's going to generate a vector that looks pretty similar to this, pretty close to this. It's eventually going to settle in based on these proportions. Okay, now, it's not maybe that clear, or maybe not that obvious what properties this matrix T should have in order to guarantee that, or if it can be guaranteed, but that's exactly the type of question that we're gonna talk about with this stuff. Okay, so natural question. Long-term behavior. Now, let's go back to our original example. Which was a 2x2 transition matrix. The original example we gave that led to us describing this type of problem here is 0.90, 0.05, 0.10, and 0.95. And we began with with an initial data vector of 0.7, 0.3. Okay. So let's see what the long-term behavior would be for the situation where this is your transition matrix. So you only have two states, right? States 1 and 2. And this is your initial distribution. So what is this? This is, we already computed this before. This is 0.6450 and 0.3550. Okay. Again. So hit it again with t. So t squared times x naught is 0.5983, 0.4017. What about t to the 10 times x naught. Well, we have to approximate this because we're going to be approximating the entries in t to the 10. What do I get here? This is like 0.4055, 0.5945. What about after 100 time steps? What does this look like? Again, this is approximately 0.3333 and 0.6667. One more, just for good measure. What about at the 1000th time step? It's the same as the last case. And note, since these agree, we could say that by this point at least, this has settled, right? Now, of course, what we imply when we use the word settle like this is that there's some kind of convergence, there's some kind of, we have found a limit of a thing, right? Okay, so then what does this look like, right? So it looks like this settles when 1/3 of the population is in state 1 and 2/3 is in state 2. Now, if we're being really precise here about what this means, right? When I say the word settle, as I say, we're saying that a limit exists here. So we're saying like two things here, right? So one, we're saying that the limit as n goes to infinity of t to the n times x naught is equal to the vector 1/3, 2/3 for this x naught. And secondly, that if I apply t to the vector 1/3, 2/3, what do you think is going to happen? It should fix that vector. Why? Well, I mean, if I've chosen some other initial data vector, and at the end of this limiting process, I found that actually, eventually, it gets transformed into 1/3, 2/3, and that's where it settles. Okay, then 1/3, 2/3 chosen as like my initial vector should immediately settle in the sense that it should be fixed by t. T should send it to itself, right? So you can think about that for a second. That's why that's the case, because of course the x naught that we chose is this thing, right? The x naught we chose is this thing, and we found through experience, right, through experimental data of just doing this, that it appears that the limit of this process is this vector 1/3, 2/3. So if we begin with that vector, well, you can just test it out. You can multiply t by this vector and see that, ah, yes, it actually does, in fact, fix this thing. Now, what if we tried a different x naught? Question. What if we change x naught? Well, let's repeat this example, changing that initial vector. So let t be as before. And let x naught be very different distribution. So 0.05 and 0.95. So this is still one of these probability vectors, right, that sums to 1 here, right? Its entry sum to 1. Okay, but this is a very different distribution than what we started with in this example, right? Okay, so let's see how this goes. Well, t times x naught in this case is 0.0925, 0.9075, and t to the 10 times x naught is 0.2776, 0.7224, and t to the 100 times x naught is approximately 0.3333, 0.6667, and t to the 1000 times x naught is approximately the same thing. Well, that's interesting, right? So this seems to be limiting to the same vector, even if we started with a very different, not just different, vector x naught. Well, on the first day of lecture, when I was doing this review, this bit might have been in the second day when I was finishing up some of that review. Might have been the first, I don't remember which day I covered it in, but it's in that initial review that I did at the beginning of the semester. I mentioned that the power of using eigenvalues and eigenvectors in analyzing the behavior of these situations where you're modeling it through iterated matrix multiplication. The power is that all of the things that happen, all of the behavior is determined by the eigenvalues and eigenvectors of the matrix itself. So that this initial vector is not actually what's mattering here, right? What is mattering more is some quantity associated with the matrix itself. Okay, as we're going to see, that is going to be a particular eigenvector for the eigenvalue 1. Now you might say, well, not every matrix has eigenvalue 1, and that's very true. So we have a lot of stuff that we have to do in order to phrase all of this analysis that we want to do. So we have to revisit and also introduce some new stuff. Some theory in order to be able to talk about any of this stuff. Okay, so in order to say what's going on here, we've got to introduce some things. So let's do that now. First, start with the definition. We gave these things names, but we didn't actually write it down. I just kind of said it. A probability vector is a vector whose entries lie between 0 and 1 and add to 1. is entries. We'll call them V sub I just because. So the entries satisfy that they're all between 0 and 1, and they sum to 1. Okay. So we have, using the notation I've used here, we have a vector with n entries. Each of those entries are between 0 and 1, and they sum to 1. Now you might say, why are you including 1 here? Obviously, if any entry is equal to 1, the rest have to be 0. Yes, but that's fine. I want to include that in this analysis. Okay. Next. What is a transition matrix? A transition matrix, or sometimes it's called a stochastic matrix, or a Markov matrix. Now, we called this entire discussion Markov chains, but I haven't actually used the expression Markov chain or described what a Markov chain is yet. Don't worry, we're we're getting there. Okay. So a transition matrix, or stochastic matrix, or Markov matrix is a matrix in which each column is a probability vector. So we noticed this about the matrices T that we did yesterday, right? In both examples, in both of those cases, the columns sum to 1. This made sense in the context of the problem, right? How we had to set up the problem, because they needed to sum to 1 because you needed to know where everyone was going, whether everyone was staying in the state that they were already in or whether they were moving to another state, right? That was the point. Okay. Now, so example, an example R, that sounds strange. An example is the matrix T from earlier. Now that actually refers to 2 examples, but whatever. All right, we're not going to keep getting caught up on plurals here. This, recall that in these examples, T sub ij was equal to the proportion of people that move from state j to state I in 1 step. Now, you might have noticed, especially if you've seen this otherwise, that we've used some strange words. Well, I mean, maybe proportion's not that strange of a word, but we've used words that are dancing around what is happening here. The word stochastic comes up, you know that probability is involved. So, of course, thinking about these as probabilities is going to be natural, right? And maybe going to be the most common context in which this stuff comes up. Of course, that's ultimately what we are doing with Markov chains. Like very quickly, like a Markov chain is a process where essentially you have transitions between states, and to go from one state to the next, you only need to know essentially the info at one stage. So I'll talk about that formally when I actually define what a Markov chain is, but that's just letting you see a little bit under the hood as to where this stuff is going. Okay, so we have some more definitions. So next definition. A probability vector is a steady state vector for a transition matrix T if it is fixed by T. So maybe we'll say a probability vector X is a steady state vector for a transition matrix T if T times X is equal to X. Note, this is an eigenvector for T corresponding to eigenvalue lambda equals 1. All right, we've seen this before. Now, I want to note something here because this can be confusing for some of the statements that I am about to make soon. Note, a steady state vector is a probability vector. That's included in the definition here. A steady state vector has to already be a probability vector, which means that its entries already have to sum to 1. The reason why this is actually important is there's a statement that I'm going to make about the uniqueness of steady state vectors for certain matrices. And based on what you know about eigenvectors, namely that eigenvectors are not unique, might seem like there's a bit of a contradiction here. But so then the fact that this is actually a probability vector is crucial because it's the thing that gives you the uniqueness. Okay, without that, there would not be the uniqueness here because generally, as I've mentioned several times at this point, eigenvectors are not unique for a particular eigenvalue. Okay. I need one more definition, then I can state my theorem. Okay, so one more. There's another definition. A regular transition matrix T satisfies that there is an integer k greater than or equal to 1 such that all entries in T to the k are non-zero. Note, if T itself has all non-zero entries, it is regular, since such a k is equal to 1. Okay. Okay, so if you begin with a transition matrix T that has all non-zero entries, then it is regular. So in fact, here is the 3x3 example that we did earlier. All the entries of T are non-zero. It's regular. Here's the 2 by 2 example we did. Every entry is non-zero. It's regular. Okay. So, what does this regularity get me? So theorem, I'm not going to prove this. The notes do a proof in the 2 by 2 case, but the general case, it would take too long. It'd be too complicated to go through, so you're just going to have to accept this one. If T is a regular transition matrix, then it has lambda equals 1 as an eigenvalue, and there is a unique steady state eigenvector. We'll call it x star associated to it. Now, this is the point that I was making. Remember, for any matrix, any eigenvalue for that matrix, eigenvectors are not unique in the sense that you can scale the eigenvector by a scalar. For instance, you can also do other things depending on the dimension of the eigenspace, but the point is that you can at least scale eigenvectors by a constant, get another eigenvector for that same eigenvalue. So, but notice that we're not claiming that it's a unique eigenvector, it's a unique steady state eigenvector, which has the additional requirement that the sum of its entries is 1. So it is not unique as an eigenvector for this eigenvalue, but it is unique as a steady state eigenvector. It's the only one that is a steady state eigenvector, so that its entry sum to 1. Okay, now I'm not done here. Also, for any probability vector, x naught that we choose, the limit as k goes to infinity of t to the k x naught is exactly this steady state eigenvector. So now we have the machinery to describe what it was that was going on earlier, right? So let's go back and reconsider this example we just did. All right, so here was our 2 by 2 transition matrix. It is definitely regular because all of its entries are non-zero, so that theorem applies, which means 1 is definitely an eigenvalue. Okay. And secondly, there exists some unique eigenvector that is a steady state eigenvector associated to that eigenvalue. We know what it is. It's the vector 1/3, 2/3. Okay. So that is the unique steady state eigenvector for this thing. Now, you might say to yourself, and I'll write this out later, like, I know how to find eigenvalues and eigenvectors. How do I find steady state eigenvectors? Like, among all the eigenvectors I find, how do I make sure that it's steady state? Well, simple enough, right? Just like how it is easy or straightforward to find unit vectors given some non-zero vector, right? Making it a unit vector, scaling it to be a unit vector is simple. You just scale it by its length, right? Or by 1 over its length, rather. In the same way, you can scale the eigenvector you found by 1 over the sum of its entries. Okay, so we will talk about that here in a second. But first, so we have this. It is a steady state vector because its probability vector sums to 1 here, and it's an eigenvector for eigenvalue lambda equals 1 for this matrix T. And notice that no matter what we chose our initial vector to be, we even did another example where we picked a very different vector, right? And got the same result. So ultimately, this thing on the right, this is my steady state eigenvector. Okay. So tying up some of the things. So proof, 2x2 cases in the notes. But I'm not going to do the general case or the 2x2 case. I'll leave that for you to read if you want to see how it goes. One thing I will say here is quick corollary. So something that follows immediately from this theorem is if T is regular, then the limit as k goes to infinity of t to the k exists where the columns are all equal and all equal x star. Okay. So this thing is, we can actually compute the matrix limit using this, although we don't, this is a nice fact that just falls out of the theorem. Theorem tells us more than just this, but this is a nice fact. Okay, and so basically, what this means is that if we want to, this corollary tells us that if we want to approximate the steady state vector, for a regular, got to make sure it exists first, a regular transition matrix T, we can look at a single column, from t to the k for some large k. Okay. Now, quick question. If I find an eigenvector for lambda equals 1 for a regular transition matrix T, how can I be sure it is a steady state vector? The answer is scale it by the reciprocal of the sum of its entries. So if the vector in question is this thing, scale it by the sum of its entries, then this will necessarily be steady state. So long as this thing is an eigenvector for lambda equals 1. So this relies on two things, right? The fact that you can always scale an eigenvector by some scalar and end up with an eigenvector corresponding to the same eigenvalue. Okay, and just by the algebra here, right, this makes sure that the sum of the entries of this new vector is going to exactly be 1, because it's going to be v1 plus v2 plus and so on out to vn over exactly this in the denominator, so it's going to be 1. Okay. This is relevant because even though you're often going to be using MATLAB or some other computational tool in order to maybe find these eigenvectors quickly, what that is going to mean is that MATLAB oftentimes is going to spit out an eigenvector that is an eigenvector, but it might not be a steady state eigenvector. So you may have to scale it. In fact, you will usually have to do this. Okay. All right. So a couple of facts. Maybe I'll go ahead and just say warning here since I just mentioned it. If you use MATLAB or other tools to find this eigenvector, you will almost always have to do this scaling yourself. That is manually. After that is done, you will have to then tell MATLAB to scale it in this way, right? And that will be your output. Okay. So dividing this by the sum of its entries is exactly the way to make this work. A couple more facts, and then I want to move on to an example now that we have all this machinery to discuss this. So here's a fact. If T is a transition matrix, but is not regular, the theorem may not hold. There's no guarantee the theorem holds if this is not regular. Okay, it might, but no guarantee, so theorem might fail. Theorem only applies for a regular transition matrix, so let's just go back. Let me put the theorem back on the screen here. If T is a regular transition matrix, this is the main assumption being made. Okay, so that is important. All right, so this theorem may not hold if T is not regular. Okay, which remember, the theorem states that T has a 1 as an eigenvalue. So you already know, like, there's no reason why a random matrix is going to have 1 as an eigenvalue. But also, you might say, well, okay, T is not exactly a random matrix. It's a transition matrix, so that it's not just any old matrix. It at least has some restrictions. But even that is not enough to say that it has to have 1 as an eigenvalue. In fact, if 0 entries are allowed, you could have, you know, there are matrices you could cook up where this is more of a problem. Okay. All right. So that's one thing to be aware of. Another fact is that a transition matrix that's not regular might have more than one steady state vector, and there are no guarantees about limiting behavior. So this is another way in which the theorem could be false. So a transition matrix that is not regular may have more than one steady state vector. I mean, it might not have any, right? It might not have one as an eigenvalue, so it might not have a single one, but it also might have more than one. So it might have more than one steady state vector, and thus there are no guarantees about limiting behavior. So this analysis that we would very much like to do about the limit of this process, we're now unable to do if it has more than one steady state vector. Okay. So these are just things to keep in mind. Now, let's return to an earlier example. So our 3x3 example from earlier. Here we go. So here's our matrix T. Okay. We've already noticed this is regular for the simple reason that all of its entries are non-zero, which means that if we choose k equals 1, then we have our positive integer k such that t to the k has no zero entries. So here it is. So this is regular. What are its eigenvalues? I'm going to write them here. Oh, I'll write them here. So T has eigenvalues. Again, you could find these with MATLAB or your favorite eigenvalue calculation machine. So T has eigenvalues. We'll say lambda 1 is 1, and lambda 2 is like 0.763246, and lambda 3 is 0.636754. Now remember, eigenvalues are roots of polynomials, right? So if you're saying, hey, I remember eigenvalues, everything was 1, 2, and 3, or -5, or 0, or 15. Well, of course, selection bias, because we want you to be able to deal with things by hand when you're taking a Math 240 exam, but frequently, eigenvalues are roots of polynomials, and roots of polynomials can be, frequently are irrational numbers, right? Square root of 2. And so, your eigenvalues are, maybe typically going to be pretty nasty. But anyway, really, of course, the eigenvalue we care about is just this first one, because that's the thing that gives us our. We also knew that that one existed just from the fact that this is regular by the theorem. So we know that there is going to be an eigenvector that is going to be a probability vector for which this works. So let's just use MATLAB. So using MATLAB, right? To find eigenvector for t for the eigenvalue lambda equals 1, MATLAB will spit out the following vector, which is 0.886659, 0.33 39013 and 0.248264, something like that. Notice this is not actually a probability vector. And just to do this one more time, I'm sorry for repeating myself, but this is the point. A steady state vector has to be a probability vector, and I made a special note of that. So here, this not being a probability vector, it needs to be. So what do? Scale it 1 over sum of entries. Right, which is going to give us the following. So we scale this eigenvector by 1 over the sum of its entries. This gives us 0.581397, 0.255815, and 0.16791. Sure, everybody noticed that. Now, this is our unique steady state vector for this problem, which means that this is the limit, right? So this is the limit as k goes to infinity of t to the k times any initial data vector x naught whatsoever, so long as it's a probability vector. So then what does this tell me in the context of the problem that I am interested in? Right, so what does this tell me? Well, so going all the way back, putting this problem back on here. Whoop, what did I do with it? Here we go. So here's my original diagram showing what's going on with these three states. Here's my transition matrix. But let's say I ask what will be the final? What's the limiting distribution? Right? What is the limiting situation for this state of affairs? And the answer is just reading directly off this vector. This means that 58% of the population will end up in 1, and you could be more accurate here and say, 58.1397. So 58% of population ends up in state 1. 26% of the population ends up in state 2. And 16% of population ends up in state 3. This allows you to give like a full analysis of how this would end. Okay, again, end, right? This is our limiting behavior. This is like the asymptotic behavior of this model. Okay. Now, what I want you to do is you can check the corollary. That is, pick your favorite, say, do it for like t to the 2000. All right, that's not any kind of Terminator reference or anything. This is here, check this t to the 2000th power. What should this look like? Its columns should be a 3 by 3 matrix, all of whose columns look like this. Okay. That's what should be happening there. Okay. Now, this is very, very nice, since this allows us to immediately finish basically this analysis that we're doing if we know that t is regular. So we have this theorem that basically spits out exactly what we want. We know we have lambda equals 1 as an eigenvalue, which means pick your favorite eigenvector associated to it, scale it, right, by 1 over the sum of its entries. You get your steady state vector that is unique, and that is the limiting vector. That is what this process limits to. That's great, but a couple of questions remain, which is, can I always be expected to be dealing with a regular transition matrix? The answer is no. But then what does it mean for T to be non-regular, right? So, question. I mean, we know how to answer this in a very clean way, which is just saying, well, um, this means that we have a matrix that there does not exist a k for which t to the k always has at least one, or always has all non-zero entries. Um, well, maybe you don't say that that's that clean, right? Which is part of the joke. We don't have a good way of describing what this. We know what it means mathematically, like in words, but what does this actually, if we're trying to interpret what such a thing would look like, how is this? So maybe if I just write this out, you see how awkward this is, right? It means uh, if t is non-regular, then t to the k has at least one zero entry for all integers k greater than or equal to 1. But I'm basically just going to ask this question again. What does this actually mean? So in order to see this, we need to look at the powers of t and what is going on here. So let's write out our generic transition matrix T, and let's use the notation we used previously, which is T sub 1, 1, T sub 1, 2, T sub 1, 3, and so on, out to T sub 1 n. This goes all the way down to T sub n n. This goes all the way down to T sub n1, and all the way over to T sub n n. So this is my typical matrix notation here. Okay. Now, what do we know? We know, we have written before, that T sub ij equals what? This is proportion of people that move from state j to state I in one iteration, in one step. I've been saying this the whole time, and maybe it seems like I'm being needlessly like verbose here by phrasing it this way, but I'm really not, and you're about to see why I've been phrasing it this way the whole time. Okay, but what does the ij entry in t squared look like? So what does the ij entry in t squared look like? Well, the ij entry in t squared, if I multiplied t by itself, by t here, and looked at the ijth entry in that matrix multiplication using, if you like, your ij, right, definition of entry by entry matrix multiplication, then the answer is t squared sub ij looks like t I1 t1 I, or sorry, 1j plus T I2 T 2j plus, and so on in this same fashion. The last entry would be T sub I n T sub nj. Now, what do you notice about this? What is this? So let's start here. So 1, what is T sub I1 times T sub 1j? This is the proportion of people that move from state j to state 1, and then from state 1 to state j. Or sorry, state I here. So proportion of people that move from state j to state 1, and then from state 1 to state I. Similarly, T sub I2 times T sub 2j is the proportion of people that move from state j to state 2, then state 2 to state I. And so on, all the way out to the last entry here in the sum, which would be the proportion of people that move from state j to state n, and then from state n to state I. Taking all of this together, and we're summing each of these here, so there's n elements in this sum. Okay, what am I doing? I'm summing the total proportion of people moving from state j to state I in 2 iterations. Okay, exactly 2 iterations. So, and this is showing all of the ways they can do this. They can move from state j to state 1, and then from 1 to I, j to 2, then 2 to I, j to 3, then 3 to I, all the way out to j to n, and then n to I. So summing all of these, what this means, rewriting it. All right, so I just said it in words, but now let's write it out here. What is this? This is the proportion of people that move from state j to state I in exactly 2 iterations. Similarly, I'm going to go ahead and say you can write out the same thing here. This is the proportion of people that move from state j to state I in exactly 3 iterations. So that we can state exactly what this means. And so now you see why I've been saying this over and over again about our transition matrix T, because our transition matrix T is a T to the K where K is just equal to 1. So this is each of the entries T sub ij is a proportion of people that move from state J to state I in exactly 1 iteration, right? So that's why I kept harping on this. Okay. So in this way, how can I think of a regular Transition matrix. If we know that the powers t to the k, and these are kind of the central object of study, really, right? So t to the k is kind of the central object of study in this whole analysis. And if I know that the entries of t to the k are laid out like this, right? Then the fact that, say, t is regular, right, means that there exists some k where these are non-zero, where every entry is non-zero, which means there exists a k for which it can be said that in exactly k iterations, some people move from every state to every other state. So there is some k for such that in exactly k iterations, some people move from every state to every other state. You know, you might say eventually, or at this step, right? That's the point. Okay. Um, well, don't need this word, I guess. We're just considering this k itself. I could have added that if I had this k. Now, the question is, what does this say about my population distribution? So, can you say that this means that the population reaches every state from each state eventually? And the answer is no, right? Note this does not say that the population reaches every state from each state eventually. And the example to show this is the following. Here, everyone, I want to caution you against using this this quote as the same as this fact. These are not equivalent things, and to see that here for this transition matrix, the states alternate, right? So everyone alternates states, but this isn't regular. So in this case, the entire population moves from one state to the other. They alternate states completely. But this is not a shorthand for being regular here, right? So I want to be careful. The converse here is not true. So that this thing that I've put in quotes here is not equivalent to this statement here that I've boxed in. Okay. Now, this gives us a condition on guaranteeing that a matrix is not regular, of course. So, however, note that if some states are not reachable from other states, So, however, note that if some states are not reachable from other states, and this means ever, not just in a single, in a single step. This just means are not reachable from other states ever. There's no way to get there. Then what this means is that the transition matrix will definitely not be regular. Since you're always going to have at least one entry that is 0. In the t to the k. For all k. But how? How do I know that, right? If state I is not reachable, from state j, that is ever, then the ijth entry of t to the k is 0 for all k. Okay. Let's see an example of this. Actually, I think here is a good time to stop, and maybe I'll draw a couple of examples here to illustrate what it is I'm going to talk about. So I'm going to go ahead and put these examples out there, and we'll refer to them tomorrow. So let's see how this goes here. Let's again do a 3x3 example. So we'll call this 3. Call this 2. So that the numbers involved here look like this. I haven't accounted for all of 1. Oh, actually, yeah, I have. I've accounted for all of 1 here. This is 100%. Let's say that this is 80%, and then 5% go to 2. For 2, I have 98% remain and 0.02. I think that's everything now. I think everything is accounted for. Before I even write out my transition matrix, okay, which I can do very quickly, before I even write it out, I can see that can I reach each state from every other state? And is that enough to tell me that I'm good to go? In fact, that's enough to tell me I'm good to go immediately before I even write out t. Or is it? Is there a 0 in this? Is there a state that is unreachable in one step? Well, maybe, right? Let's write out t when we notice that I can't get from 1 to 2 in one step. So I'm writing out t here. I know what the diagonal entries are, right? So going from 1 to 1, going from 2 to 2, and going from 3 to 3. Now the question, going from 1 to 2 in one step, I can't get there in one step, so this is a 0. Going from 2 to 1 in one step, I can't get there in one step, so this is a 0. From 3 to 1 I read those backwards. So this is the T12 entry. So this is from 2 to 1. This is from 1 to 2, right? This is the T21 entry. So this is from 1 to 2. That's 0. From 2 to 1, that's also 0. Here, this is T13. So this is from 3 to 1. So that's 0.15. This is the T23 entry. So that's from 3 to 2. So that's 0.05. This is T31, so that's 1 to 3, so that's 0.10. Again, you might say, well, you can tell what it is by, you know, that the column sums have to be 1, so you know what this has to be already too. But this is T32, which is from 2 to 3, which is 0.02. Okay, so now we have an example where our matrix T has zeros in these entries, right? Which indicates that I cannot get from states 1 to 2 in one step. So I can't go from 1 to 2 in one step. I can't go from 2 to 1 in one step, right? Of course, there's no reason for this symmetry necessarily. Maybe I could get from 2 to 1 in one step, but I can't get from 1 to 2 in one step. You could draw up a diagram like that. Okay. I'm going to draw another example, and I'll end with that. We'll talk more about this next time, but I'm going to end with this example. So here's 1, 2, 3, 4, 5. So for 1, 90% stay, 10% move to 3. For 2, 97% stay, 2% move to 3, and 1% move to 4. For 3, 80% stay, and 5% move to 2, and 15% move to 1. For 4, 70% stay, and 30% move to 5. 5, 75% stay, and 25% move to 4. Now, I'm going to say more about the transition matrix next time, but what I will say for now is the first thing you might notice before I even write it down. It is not regular. Why? Because once I move to, yes, there's a small chance of this happening, but once I move to state 4 here from 2, right, I can never get back. Simultaneously, if I'm in states 4 or 5, I remain in this part of the diagram forever. I can never reach 1, 2, or 3. Right? So states 1, 2, 3 are not reachable from states 4 and 5. Right? So even though regularity is not equivalent to saying that you know, that all the population reaches other states eventually, it's not equivalent to that thing. But what you can say is that if there's unreachable states from some other states, that is, they can never be reached ever in any number of steps, then T has to be non-regular. It can't be regular because you are always going to have some entry in t to the k that is 0. Okay, so I'll end with these two examples. I'm going to say more about them next time, and then we're going to talk a little bit more about these things and explicitly like what we mean when we talk about Markov chains. And finally, it's funny, we've been talking about this for days, and we're just now getting to maybe a statement of what I mean when I say Markov chain here, but it'll all be made clear next time. So Friday, that is tomorrow, we'll finish up Markov chains for the most part, and move on to our next topic. Your next homework will be posted soon. It'll be due next week, and I'll have more announcements about office hours and things like that later. So just stick to Elms. Be looking out for Elms announcements, because every homework will be accompanied by an Elms announcement, so you're not going to miss it or anything. But anyway, I will see you all then.